So in a previous example, we looked at a section similar to this, where we had a section without a web. It was about the same thickness, same size, and then we compared its torsional rigidity to another section where we had the same outer dimensions, except we had a web directly in the center. And then we compared it to a third case where this web was slightly scooted over about 5 centimeters, such that L1 was 5 centimeters, L2 was 15, and L3 was 10 centimeters. And essentially what we did was we were figuring out how the torsional rigidity compared by adding that web and then scooting it over 5 centimeters to the left, and then comparing that to the structure, the section without the web. And in the end, we found out that with having the web directly in the center, same thickness as the outer structure, it actually had the same torsional constant as the original structure without webbing. And then when we moved the webbing 5 centimeters to the left, it only increased the torsional constant by about 14.29 centimeters to the fourth. So essentially for this problem, it'll be a very similar start where we'll start out using Brett's equation, and we can use this modification of Brett's equation because we have a constant thickness all the way throughout. And then with the overall torque throughout the structure, that's essentially the summation of 2 times the shear flow of the first section times the essentially area of the first section, and then also having the 2 times the shear flow of the second section times the area of the second section. And we're just adding those up together. And then here, A is L1 times L3, and A2 is L2 times L3. And then the next thing that we did in the previous problem was we then solved for the twist rates, where essentially the twist rate is 1 divided by 2 times your shear modulus times the area of that section, and then you multiply by the closed integral of your shear flow times ds divided by t. But in the previous problem, we had a constant thickness similar to this, so we could actually pull out t and substitute a. And then what we did was we essentially found the perimeter, or the distance that each shear flow traveled throughout each cell. Whereas with Q1, it's going to travel through a L1 distance, L3 distance, and a L1 distance. Now what we're going through now is for the completely closed example that we had. So if you imagine that this section is not cut open, that's essentially what we're going through now. But yeah, anyways, so Q1, it went through an L1, L3, L1, and then Q12, where Q12 is equal to Q1 minus Q2. We also went through the steps in that in the previous video. That's traveling through a distance of L3. And then that's how we got the twist rate 1. And then for twist rate 2, something very similar, where now we input a 2 bar, and then we start looking at the shear flow of 2, where it passes through a distance of L2, L3, and L2. So essentially I have 2L plus L3. And then we subtracted this Q12 here because Q2 is going in the opposite direction of Q12. So that's why we had minus Q1 minus Q2 in this section here, which also still travels through a distance of L3. Now the next thing that we did in the previous example was we set our twist rates equal to one another, and then we set them equal to just theta. Now this is true because of compatibility. This must be satisfied. So we said theta 1 is equal to theta 2, and then from there we're able to solve for a relation between Q1 and Q2, essentially just setting these two equations equal to one another, and then this is what we got out of it. Now the final step that we had to essentially get us caught up was we then took the equation for the torque up here, and then we substituted A1 and A2 into it, and then we essentially plugged that into the relation between the torsional constant, the torque, the shear modulus, and the twist rate. And twist rate, I just used the first twist rate here, but we should be able to use either or because they should be equal to one another. So with that being said, now we should be caught up to the current problem. So in the current problem, what we want to do is we want to calculate the torsional rigidity for both the uncut and the cut essentially structure. So we can imagine if this section was not cut, we want to calculate the torsional rigidity of the entire thing. And then we want to do it again, except leaving this cut there and then calculating the torsional rigidity of the entire structure. So we're going to do exactly that. But first, we're going to start out with the uncut web. So we'll say for the uncut webs, so in this case we had L1 is equal to L2, which is equal to L3, and that's given to us to be 10 centimeters, and that's going to be equal to L. So what we can do is we can use the equation, or I'd rather say the relation between Q2 and Q1 up here to figure out how they relate. So we can say Q2 is going to be equal to 2 plus 2 times 10 divided by 10 plus 10 divided by 10. And then notice we're going to have the same thing in the numerator and the denominator. And then this will all be multiplied by Q1. So we can actually say that Q2 is going to be equal to Q1. So then what we can do is we can start to write out what the torsional constant will be for the uncut webs. So what I'm going to do is I'm going to replace all the L's with just L, just to make things a little bit simpler because they'll be the same length. And then I'm going to replace all of the Q's with just Q, because Q1 and Q2 are equal to one another here. So they have no factor or anything between them. So what we can do is we get 4L squared, and then we get QL squared plus QL squared times the thickness, T, and then we'll divide by 3LQ. So essentially have 2 plus 2 minus 1 of QL. And then we can do some simplification. So we can cancel out the Q's, and then we can cancel out 1L here. So we should get 8/3 times L cubed times T, and that should be equal to 8/3 times 10 centimeters cubed times a thickness of 0.3 centimeters, and that should give us about 800 centimeters to the fourth. So this is going to be the torsional constant for the original structure. And then we can say, so for the original torsional rigidity, that's going to be our torsional constant times the shear modulus. That'll be 800 times G centimeters to the fourth. So now we can start looking at what happens if we were to cut that left side, or that left wall of the structure. So like this right here. So if we were to cut that, what would that look like? So now we can start to say, for the cut web, so our torsional constant, it's actually going to change slightly. So I'll say the J2 cell cut, so for the entire structure, including both cells with one of them cut, that is going to be equal to the cell that is uncut plus the cell that is cut. So let's draw this out real quick of what we have. So we have, should be kind of square-like, and then we'll have a height of L3, and then we'll have a width of L2 for the uncut section, and then for the cut section, so something that looks kind of like this, because we don't want to overlap our sides. We don't want to double count anything. And that'll have a length of L1, except in the kind of centerish here, we'll have a cut. So let's add a little gap there. There we go. So now what we can say is we can say that the torsional constant of the two-cell cut, so for the first one here, notice it's closed, we have the uniform thickness, so instantly we should be thinking Brett's equation. We can use that, that makes our life easy. Let's absolutely do that. So remember, with Brett's equation, that was 4a bar squared times thickness divided by the perimeter, or the perimeter length. And then for the cut section, what we're actually going to do here is we're going to have the summation of I. We'll have 1/3 times the length of each bar times the thickness of each bar cubed. So essentially what that'll get us is the area of the uncut section. That's it's going to be 10 centimeters times 10 centimeters. So we'll have 100 centimeters squared, all that squared. And then we'll multiply by 0.3 centimeters for the thickness. And then for the perimeter, we'll just have 2 times 10 plus 10. So we'll have 2 times 20 centimeters. And then for this next part, so essentially B, that's going to be the length of our pieces, or our bars here. And then T, that's going to be the thickness of the bars. Now they all have the same thickness, they all have the same length. So what we can say is we can say 3 times 1/3, we'll have 10 centimeters for the length, and then a thickness of 0.3 centimeters cubed. And then what we should get is a J2 cell cut equal to 300.27 centimeters to the 4. And just for perspective, I want to point out that this section right here, that is 300 centimeters to the 4th. And then over here, this section is 0.27 centimeters to the 4th. So notice when we make that cut in our bar, we lose a lot in terms of our torsional constant, which will greatly impact our torsional rigidity, or essentially the stiffness of it. And the problem with that is, well, it makes it weaker in the end. And what we can do is we can actually calculate this percent of reduction in JG. So let's do that now. So essentially I have R as the reduction. It's going to be 800 minus 300.27 divided by 800 times 100%. So we get a reduction in torsional rigidity of about 62.5%, which that is pretty significant compared to the original.